Hello, students. Welcome to Chapter 3, Eclipses and the Motion of the Moon. In this, we'll talk about uh, the motion of the moon, how it moves, about its rotation, about its trajectory around the Earth, its phases, etc. And we will talk about eclipses because both the kind of eclipses, the solar eclipse and lunar eclipse, happen because of the involvement of the moon. So in this chapter, the important things to pay attention are the phases. We always see the same side of the moon. Why is that? Difference between lunar and solar eclipse. Why not all lunar eclipses are total eclipses. Solar eclipses you can only see from some places on Earth, whereas lunar eclipse, when it happens, you can see a whole hemisphere of the Earth, which is experiencing nighttime, can see the lunar eclipse. In fact, more than that. And in the end, we'll talk about ancient Greek astronomers and how they found the sizes of Earth, moon, and the sun. So here are the phases of the moon. So moon goes through a cycle. When it starts out, it's really small. Here it starts at A, and that is called new moon. And then it goes through all these phases. It gets bigger, 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 gets to the maximum size, which we call the full moon. And then it decreases, decreases, decreases until it becomes the new moon. Okay, so first, I want to tell you about the naming convention of the phases. So the smallest new one is called the smallest one at the beginning of the cycle is called new moon. And by the way, this cycle is about 29.5 days. And so something to think about, our calendar of weeks, years, months is made up of, because of these astronomical cycles. So the month, we divided the year into months because of the lunar cycle. So 29.5, nearly 30. That's why months are about 30 days. Okay. Now the phases. Let me just say the names of these phases first, and then I'll tell you some more patterns in there. So new moon, waxing crescent moon, first quarter moon, waxing gibbous moon, full moon, waning gibbous moon, third quarter moon, waning crescent moon, and then new moon again. Why are these called what they are called? Well, new moon is new moon, right? After it almost reduces to zero size, it's starting to grow again, so new moon. Then full moon, obviously, it looks full. You can see a full circle, so it's called full moon. Then there's the first quarter. You can think of the whole cycle. And so at this point, when you see half the moon, half the circle, that is the first quarter, so-called first quarter moon, and then the third quarter moon. So those are most easy to understand. And then waxing and waning. So these two words you should understand. When the moon is in the growing phase, it's called waxing. And when it is in the decreasing phases, it is called waning. So that's that. And then I'm sure you have heard the word crescent, and you know that. So when it is in the crescent shape and it is increasing in size, this phase is called waxing crescent. Then after the first quarter, gibbous. Gibbous means swollen. Okay, so they imagined it as being, swelling in the ancient times. So this is waxing gibbous moon, then waning gibbous moon, third quarter moon, waning crescent moon. So those are all the phases. Now, why do these phases happen? I think in today's world, students and general people are more and more aware of the reason for phases, but there was a lot of confusion about why the phases of moon are. Well, in really ancient times, they used to really think that the moon grows and and shrinks. But then they understood that it is only a part of the moon that they are seeing because of how much it is illuminated. But then the misconception was that somehow the Earth's shadow is falling on the moon, and that's why we are only able to see part of it, and that's why we see the phases. Well, that is wrong. When the Earth's shadow falls on the moon, that is when a lunar eclipse happens. But at other times, we see the phases because in reality, although always, pretty much always, except in lunar eclipse, half of the moon is always illuminated by the sun, and the other half is always dark. But as it is going around the Earth, we are able to see different amounts of that illuminated side. And that is why we see the phases. For example, in this diagram, the sun is towards the top right corner, and the moon is sort of in between the Earth and the sun. So the illuminated side is facing away from the Earth. So we see a very small amount of the illuminated side just because of a little bit of a misalignment. And from that, you can see how as it moves to different positions, we are able to see more and more of the illuminated side. That is what causes phases. Okay. The other misconception is that you can see moon only at night, and that is wrong. Maybe it's more conspicuous in the night, but turns out that you can see the moon in the sky at pretty much all times of the day. If you just pay attention, you will be able to see, sometimes you'll be able to see the moon somewhere in the sky, even at noon. Which phase it is in, the phase of the moon, determines when you will see the moon in the sky, whether you will see it in the day or whether you will see it in the night. These phases here, just from the diagram, these phases here, A, B, H, all of these phases over here, even C and G, these you'll be able to see even when it's light outside. You'll be able to see these phases in the sky, the moon in the sky. Okay. Whereas these phases, the waxing gibbous, the full moon, the waning gibbous, these will be present in the sky more at night. And if you look carefully at this diagram, you can clearly see the geometry here. The phases A, B, H, these are pointing towards the illuminated side of the Earth. That means that when the moon is in those places, then people who are experiencing daytime, they can see the moon. Whereas when it is in the phases D, E, and F, then it's the people in the unilluminated side, which is the people experiencing nighttime, they can see those phases of the moon. So the moon remains in the sky. It rises and it sets. It remains in the sky for about 12 hours. And it rises at different times and sets at different times. And that is what determines if it will be in the sky primarily during the day or half day, half night, or primarily during the night time. The full moon rises exactly when the sun sets. When on the day when it's full moon, moon rises exactly on the day when exactly at the moment that the sun sets. Okay. Further on, each next day, the moon rises 50 minutes later. Okay, so suppose today was a full moon and the moon rose at 6 p.m. Tomorrow, the moon will rise at 6:50 p.m. And then after that, it will rise at 7:40 p.m., then 8:30 p.m., then 9:20 p.m., and so on. Okay. So some diagrams here trying to explain more how the phases are seen. Another point, we always see only the one face of the moon. We always see one side of the moon. We don't see the other side. And so the side that we see is called the near side of the moon, and the other side is called the far side of the moon. And standing here on Earth, just looking directly at the moon, we can never see the far side of the moon. And for thousands of years, we didn't see that. We didn't see the far side of the moon. But now we have been able to see it when we sent probes to circle the moon. They went around the moon and they took images. That's how we see the far side of the moon. But normally when we stand here on Earth and look at the moon, we only see the near side. And why is that? Does that mean that the moon does not rotate? Actually, that's not correct. And these two diagrams show, first diagram shows that if the moon actually did not rotate, then we would be able to see both sides. We'll be able to see all sides of the moon. Turns out the moon does rotate, and it rotates in synchrony with its orbit around the Earth. So, so as you can see in this diagram, when it does a quarter of its orbit, it also spins in this direction by a quarter rotation. And that is what makes it possible for the moon to keep the same face towards the Earth. Sidereal and synodic months. Remember, we had the sidereal and solar day. Similarly, when it comes to the moon, there's this sidereal and synodic month. So sidereal month is the time in which the moon completes one full 360-degree rotation around the Earth. And if you look at these two diagrams, it goes from we start from the new moon, when the moon is approximately in a straight line with the sun and the Earth. And then as the Earth is moving, the moon is circling around. And when it comes back to this direction, to the parallel line, then it has completed its 360-degree rotation. And that is the actual 360-degree rotation that we call sidereal month. And the moon does that in about 27 days. Somewhere I've noted the exact number of days. It's about 27 days. However, standing here on Earth, how ancient people imagined the cycle of the moon, they were looking at the cycle from new moon to new moon. And for new moon to happen, the moon has to turn a little bit more to realign, to be in between the sun and the Earth. Okay, and so that makes it to about 29.5 days, and that amount of time is called synodic month. Here, I have noted it here. The sidereal month is 27.32 days. Okay, so question, when the moon is in between the Earth and the sun, why doesn't the moon block the light of the sun and cause a solar eclipse? Every month it does that. Every month the moon is in this location, it should block the sun for a little bit, cause solar eclipse. Every month we should have solar eclipse, and then at the same time when the moon is on the other side, Earth's shadow should fall on the moon, causing lunar eclipse. But that doesn't happen. Why is that? Because the plane of moon's orbit makes a 5-degree angle with the Earth's orbit. So even if the moon is in a direction which is aligned with the Earth-Sun line, it's possible that because of this plane, it's either above the plane of Earth's orbit, which is called ecliptic plane, or it is below. So in both those cases, all that will happen is you will only see the new moon or the full moon, but there won't actually be an eclipse. But there is a line of intersection between these two planes, and that line of intersections is called line of nodes. And there's the ascending node and the descending node. And when the moon is going through here, and that means it is in the ecliptic plane of the Earth, that's when, if that aligns with a new moon or a full moon, that causes an eclipse. And that is the reason this plane of the Earth's orbit is called ecliptic plane. So this kind of alignment only happens a very few times in the whole year. So as you can see, this whole line of nodes has a sort of an alignment with the Earth's orbit around the sun. So the bottom left and top right corners, that's sort of the direction of the line of nodes. And when the Earth is going through that area, that is when, if a new moon or a full moon happens, there's likelihood of eclipses happening. At other times, it does not happen. Now, let's talk about lunar eclipse. So lunar eclipse is when the moon is on the outside, and in going through the outside, the Earth blocks the light from getting to the moon. And so usually when the moon is in that position, it is quite close to being full, or actually full. It's full moon. Okay. But when it goes through the Earth's shadow, then obviously it becomes dark, and that is lunar eclipse. Now, there are these several types of lunar eclipse that can happen. First, look at the Earth's shadow. Depending on, there is a region where all of the light from the sun is blocked. That is called umbra. There are regions where the sun is blocked partially, and that is called penumbra. So depending on how above or how below the ecliptic plane the moon is, it could pass through umbra, it could pass through penumbra, or it could be partially in both the regions. So there is a total lunar eclipse when it goes through the umbra. When it totally goes through the penumbra, then it is called a penumbral eclipse. And when it goes partially through the umbra, then it is called a partial eclipse. So the and the Earth's shadow, as you can see, is quite big compared to the moon. Because the Earth is big, Earth's shadow is big, and it's quite big compared to the moon. So there is more possibility of lunar eclipse happening, of moon passing through Earth's shadow, umbra or penumbra. So lunar eclipses are more common, more people have seen them. Plus, when the Earth's shadow falls on the moon literally becomes dark. It is not getting any light from the sun. It literally becomes dark. So anyone who has a view of the moon, all the people on the dark side, on the night side of the Earth, evening side, even the moon takes a few hours to pass through the shadow. And in that time, as the Earth turns, more and more people are able to look at the moon, and they are all able to observe the lunar eclipse. So you'll notice that many more people have seen lunar eclipse. You must have observed a lunar eclipse, whereas not the same with solar eclipse, as I will explain later on. solar eclipse is more of a rare event. Here is a sequence of images as the moon passes through the Earth's shadow. Here is an image of solar eclipse. In the solar eclipse, sometimes the sky gets so dark that you can see Venus. Even with solar eclipse, the sky doesn't become pitch black, not like the night, because there is the disk of the sun, which is hidden by the moon, which is blocked by the moon, but there's this part of the sun which is called corona. Normally, we don't see the corona because the disk of the sun is way, 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 way bright compared to the corona, so we don't see it. But during a solar eclipse, the moon blocks the disk, and so corona is still visible, and the light from there gets to the Earth. So here's the interesting thing. In a lunar eclipse, the moon actually becomes dark, but in a solar eclipse, the sun doesn't actually become dark. It is only the view of the sun is blocked by the moon, which comes in the path, in the way. Interestingly, as I mentioned in chapter 1, the angular size of the moon is almost equal to the angular size of the sun. So when there's just the right alignment, the moon can completely block the sun and we can have total solar eclipse. So here is the geometry of the solar eclipse, total solar eclipse. So as you can see, because the moon is smaller, it creates a smaller shadow, smaller tip of the shadow, and it is only the tip of the umbra that falls on the Earth, and only people within that region experience a total solar eclipse. And this happens for a very short time. As the Earth is spinning, that tip of the shadow traces a path, and so people in each location barely get about a minute of time in which they experience total solar eclipse. And the penumbra is much bigger, and it covers more area on the Earth, and people in the penumbra, they can only see partial solar eclipse because some of the sun is visible. Okay, towards the end, I want to talk about the methods that the ancient Greek mathematicians used to determine the size of the Earth, sun, and the moon. So first, I want to talk about Eratosthenes. Eratosthenes used the shadow created by the sun to figure out the size of the Earth. So there's this interesting story that there was this place in Syene where people knew that at the summer solstice, the sunlight was able to get all the way down into a very, very deep well. It happened only on that certain day, not the rest of the year. So that was a very curious fact happening that people knew about. And so Eratosthenes thought about it, and that meant the sun is directly overhead on Syene at that time. What he did was he measured the angle of the sun from Alexandria. So as you can see the picture here, as you can see the geometry, he obviously knew that the Earth is round, and from the geometry you can see that because of the curvature of the Earth, the vertical direction at Alexandria is pointing in a different direction. And it is not pointing directly, it's not pointing directly towards the sun. The sun is vertically up only at Syene, not at Alexandria. At Alexandria, there's an angle between the two. And that angle is the same angle as the angle of Alexandria and Syene when compared to the center of the earth. So he actually measured the angle of the sun and angle of the vertical at Alexandria, and he found it to be about 7 degrees. Okay. And then he had some people walk from Alexandria to Syene and measure the distance. So 7 degrees is about 1/50th of the whole circle. And so if that is 1/50th of the whole circle, he reasoned that the distance between Alexandria and Syene is about 1/50th of the whole circumference of the earth. And so whatever distance was measured, he multiplied that by 50, and he said that that was the circumference of the earth. And that's how he measured the size of the earth. So that was Eratosthenes' measurement. Then came Aristarchus. Aristarchus used that value of the Earth's measurement and combined that with this other fact to calculate the size of the sun and the moon. Okay. So Aristarchus knew that the sun, moon, and earth form a right triangle at first and third quarter phases. Using geometrical arguments, he calculated the relative lengths of the sides of these triangles, thereby obtaining the distances of the sun and the moon. So as you can see, at the first quarter moon and at the third quarter moon, the line of the earth and the moon and the moon and the sun should be 90 degrees. Okay. And so it forms a right angle triangle. And then he, by looking directly towards the moon and towards the sun, he was able to measure the angle, this angle here. And by knowing this angle and some properties of geometry or trigonometry, which I won't get into detail here, he was able to figure out what is the relative distance between the Earth moon and the Earth sun. What are the relative distances? And he found that the sun was about 20 times further away than where the moon is. Okay, by his calculation. And because the sun and the moon look almost equal size, then that means that the sun has to be 20 times as bigger in diameter as compared to the moon, for it to be 20 times further away and still look the same size as the moon. So that's how we approximated the relative size of the sun and the moon. Further, by looking at the comparing the shadow of the earth and the moon, shadow of the earth and the size of moon, by observing a lunar eclipse, it was found that the moon looked about 1/3 the size of the earth. So we know the size of the earth. Moon is about 1/3 the size of the earth. So we know moon size, and sun is 20 times as big as the moon. So we know the size of the moon. And that was the way he was able to calculate the size of the sun and the moon. All right. So let's, in the last slide, we'll compare how good these numbers were. So in ancient times, the value that Eratosthenes calculated was turned out to be about 13,000 kilometers. Modern value is 12,756 kilometers. So which is surprisingly good. Eratosthenes existed more than 2,000 years ago. Okay, so that value that he calculated in such an ancient time was very good. Now let's look at the moon's diameter. Now there is a little bit more variation in the moon's diameter. The original estimation was bigger because Aristarchus didn't consider the tapering of the Earth's shadow with distance. And so even though the shadow of the Earth is 3 times the size of the moon, the shadow of the Earth is actually smaller than the actual size of Earth. So when we compare to actual size of the Earth, the size of the moon is about 1/4 the size of the Earth. So if that was taken into account, we would have gotten the correct value of 3,476. That is the reason for that variation. The second thing is that this angle that he measured over here, he measured it to be about 87 degrees, but in reality, it was about 89.5 degrees. And the geometry of this triangle is such that very, 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 very tiny variations could produce a large amount of error. And so the ratio of distances to the moon and to the sun was not 1:20, but it was supposed to be 1:400. And so that created some error, but still here are the ancient numbers and the modern numbers. And just considering the size of the value, the magnitude of the quantities that they were calculating, and in such ancient times, even getting as close as they got here, that's really appreciable. So with that, this chapter is finished. Oh, this one more slide. Something to note that when you're on the moon and looking towards the Earth, Earth also shows phases. All right. So with that, this chapter is finished, and you may do the quiz, work on the quiz.